So let me see how far along I can get with this, or if I'm going to have to scroll. Yeah, I'll probably have to use the computer keyboard. Anyway, so we just start from the beginning, and then as I come to questions that the topics we've already covered, I'll just skip those. So what's the difference between quantitative and qualitative? When you think of quantitative, think of numbers. You can put a number and a unit of measure to it. That's quantitative. So if we look at these examples and say, which ones of these are quantitative observations? A piece of metal is longer than a piece of wood? No, that's qualitative because there's just no absolute measure there. Or solution 1 is darker than 2. Yeah. Liquid in beaker A is blue, and we're still qualitative. Qualitative is a general description. Liquid, the temperature of the liquid is 60 degrees. That's it right there. And of course, we got answers. That can be helpful. Let's see if I scroll up a bit. Maybe this thing will be more useful. So, what's a generally observed behavior that can be formulated in that statement? It's a natural law, right? This is the difference between a law and a theory. If you just say what happens under certain circumstances, then you're just saying you're formulating a law, a natural law. If you attempt to say why something happens, that's a theory. And it's usually accompanied by a model. Not always, but usually. Which of the following metric relationships is incorrect? So here you need to understand and remember prefixes. Right? If you've got a microliter and a liter, what's the relationship between a microliter and a liter? Well, micro is 10 to the minus 6th. So that one's correct. Because here's the base unit right here. And this, you can think of it in these terms. If you have 1 microliter, write it like that, actually 1 like that, that would be microliter. Then you take this part of the unit, say, what does that equal to? That's 10 to the minus 6. So 1 times 10 to the minus 6, and you keep the liter. I found that to be the simplest way to deal with these prefix conversions. Is what does the prefix mean? 1 gram and 10 to the 3rd kilograms. Well, that, I mean, just think about it. Does that make any sense at all? We know that a gram is less than a kilogram. So 1,000 more kilograms is not going to make it any better. So that one's obvious without even looking at the rest of it. The base unit is a gram, and a kilogram is 1,000 grams. So this is actually 1,000,000 grams. So that one's obviously wrong. And test taking technique. If you see a multiple choice set and they've all got unique answers, right, then you need whatever the question says. You don't have to interpret. And what I mean by that is something like this: at least 2 of the above. If you have some squirrely answer like that, the last one, none of the above, all of the above, 2 of the above, that type of thing, then you just look through them until you find the right answer. Once you find the right answer, you're done. You can move on to the next one. All right, what's a metric unit of length? Well, that's mass, correct? That's volume. That's not even metric. There you go. There's the meter and the kilo. So it's 1,000 meters. We found our answer. How about these prefixes, order from smallest to largest? So when I have an ordering question in a problem like this, I try to nail down the ends first. Right? What's the smallest and what's the largest in this case? Well, the smallest of these groups looks like it's a nano. Nano is the smallest, and the largest would be probably a kilo. Yeah, there's kilo. Okay, so nano on one end and kilo on the other end are your possibilities. Anything that's not that, you can throw it out. So B's gone, C's gone, D's gone. Actually, E's gone. So by doing that, we solve the problem, right? Because none of the others match that smallest and largest, and whatever's in between. If you have, say, a nano and a kilo here, and maybe another one down here, then you look to the internals and say which ones of those are in the correct order. It's a process of elimination very often. Okay. 8.1 kilograms contains how many grams? Well, that's the type of problem we were just doing, right? 8.1 kilograms is how many grams? Well, bring the grams down, and the kilo equals 1,000. So 8.1 times 10 to the third grams. How about, let's see, this one says none of these. So when you see one like that, all of these or none of these, then you got to look at every one. Convert 0.3980 meters to millimeters. You can do that with that unit trick, 0.3980 meters, and you want to go to millimeters. So now you've got to store up information here. So how many meters, how many millimeters in a meter? Milli means 1,000th of, right? So 1,000th of a meter is that like that. How many of those does it take for a meter 1,000 times? So you need the milli part is storing those first three, right? 3 positions is 1,000. So 398.0 millimeters. All right. Yep. Or the other way to do it is dimensional analysis. We talked about that. We did talk about that, didn't we? A little bit. Yeah. In this class, I think we get it in the first 2 chapters. So we could do it this way: 0.3980 meters. Now we want to convert it to millimeters. So you need a conversion factor that will cancel the meters and leave you with millimeters. So you set up your own conversion factor here. So the meters are going to cancel because that's in the numerator and this is in the denominator. What's the relationship here? Well, there are 1,000 of these in one of those. Then by canceling these, that times 10 to the third, did I do that right? Yeah, that's right. So if we say 0.3980 times 10 to the third, and we want to put that in standard notation, then you got to multiply 1,000 times this, which means the decimal's moving to the right. You got to make it bigger. So it goes 1, 2, 3. There we go, 398. So there's more than one way to solve this problem. All right. We don't need to do that one again. Oh, this is good. What is the measure of resistance an object has to change in its state of motion? There's a word for that. Called inertia. When I think of inertia, I always think of a set table on a tablecloth. One of those satin tablecloths should be low friction. And you just take the tablecloth and jerk it out from under and everything just stays right there. If you do it right and quick enough. So everything on that table except the tablecloth has its own inertia and it prefers not to move. Right? That's Newton's first law. A stationary object tends to remain at rest unless acted upon. And object in motion tends to remain in motion in a straight line unless acted upon. So that's an expression of inertia. Oh, mass. Another way of saying inertia is mass. And it all depends. Mass is an expression of how much substance is there. Right? It doesn't change anywhere in the universe. Weight changes. It depends on the size of the mass that you're close to. Your weight will change. So I'm 200 pounds on the surface of the Earth, and that'd be 35 pounds on the surface of the moon. Let's see. Oh, this is a good one. The degree of agreement among several measurements of the same quantity. So what we're doing here is we're saying, what is it, accuracy or is it precision? So if you got several measurements and you're saying how close are they to each other, that's precision. The other one, accuracy, is how close are you to the true value or the accepted value. Okay. All right, here's an actual data set. And we want to say something about the accuracy and the precision of this data set. So we have more than one measurement, so we can draw some conclusion about the precision. The values that are measured here are supposed to be 1 gram. So how accurate is that measurement? It's not. It's not accurate at all. But the precision is pretty good, right? It's only off by 1,000th here. This is another way of expressing the precision of a measurement. Is plus or minus this value. It's called a confidence interval. So you're saying with that first one, 1.201 plus or minus 0.001, you're saying that you have confidence that your measurement is between 1.200 and 1.202. The only thing about this is it didn't say how confident are you. 95% confident, 99% confident. It doesn't say the usual confidence is 95%. But in this case, it's not accurate, but it is precise. Okay. So which one would that be? Precise, but inaccurate. There you go. That would be C. All right, we've done the dartboard. Actually, that's not a dartboard. That looks like a gun target, probably. Or it could be shooting marbles with your slingshot. Okay, let's see. I missed one. This might be worth looking at. Number 14. Scroll down a little bit. If we catch 2 of them. I don't know if we'll look at even one of them. We may not look at the second one, but the first one says you measure water in 2 containers. So I think what we're getting at here is to recognize when you're in the lab, how confident are you in your measurement? You can only be accurate. You can only express accuracy based upon the least accurate instrument in the sequence of measurements. So if you have a 10 milliliter graduated cylinder with marks at every milliliter, okay. So we have a 10 mil cylinder, so it's 10 mils at the top here. And there are marks at every 1 mil. So this would be like 3, 4, 5, 6, 7, 8, 9, 10. That's 1. Marks at every mill. Okay, so that's all the marks you have right there. And then you have one that's 1 mil marked at every point. So 1 mil, let's make it the same height. But it'd have to be thinner, wouldn't it? So this one is marked at 1 mil total. And this one is 0.1. Those are supposed to be evenly spaced. Oh, that's a pipette, excuse me. There you go. If you have some water in each of the containers and add them together, what decimal place could you report the total volume of water? Well, if this is marked off as tenths, but that one's only marked off at 1 mil, then that's as accurate as you can get. Actually, that's not right. Remember our discussion on certain and uncertain digits in a number, right? Where could we estimate? Say we have right there. That's the level of our water. Well, it'd be 1, 2, 3, 4, 5, 5.5. Whereas if we did this one, it would be 0.55. Right? Because the last one is a guess. We don't have a mark in here for tenths, but we are going to guess. So actually that was wrong. It should be B. And that's missing. That should be 0.01, I bet. 0.01. So let me make myself a note to correct that one. And this brings up another point. Yeah, I did mark it in here. If a question like this occurs on an exam and you reason the answer correctly this way, and say, in this case, you would put B as your answer. If I mark it wrong because my key says it's C, then you can come get your point. Right? Because you would be right. It should be B. Simply because drawing this picture, we see that our guess is on the tenths. That's the uncertain number. And here the guess is on the hundreds. Okay. We better look at that one also. Number 16. Here we go. The amount of uncertainty in the measured quantity is determined by what? The skill of the observer or limitations of the instrumentation? Actually, both. You're going to have defined limits on your instrumentation. And then the observer is pretty variable. Someone using the instrument will have variable, sometimes widely variable skill set. How well do they operate the instrument? That's why when I was active in soil testing in the southeastern United States, we had 10 state soil testing labs that were part of this working group. And we'd have one sample that was prepared by one of the labs, and they would subdivide it. Once it was well mixed, they would subdivide it, send those samples off to every lab. And we do a set of analyses on it and compile the data before our next meeting. And they varied quite a bit. So how do you deal with that? Well, if you want the accepted value to be a certain number, and this is our only group, we're working within this group, then you just you look at the numbers and say, okay, that's a good number, that's a good number, that's a good number. And if one of the members of the group said, we had trouble with this value. Throw that one out. That's known as an outlier. And then you would average the ones that you consider good. But it's all consensus of the working group. And that's where where you get both limitations. Instrumentation varies from one lab to another, plus the expertise varies. So that's why the answer to this one is A. So how do you round this one off to 4 significant digits? Well, the first 2 are not significant, correct? So you start counting here. 1, 2, 3, 4. And you look to the right of that. That's greater than 5. So it's actually 0.04501. 0.04501. There you go. How about this one? Express this one in scientific notation. What do you do with these leading zeros when you write your coefficient? They disappear. If you move the decimal to the right, you're storing up information as an exponent of 10. But is it getting bigger or smaller? If you move the decimal to the right, you're storing up negative powers of 10. Because the coefficient is getting bigger, that means the power of 10 has to be getting smaller. So if you move it to the right 4 places to make the coefficient between 1 and 10, then you've moved it 4 negative positions. So it should be this one right here. Okay. Let's see. Yeah, that's another scientific notation. Let's skip those. This is just a check. Remember, all your certain digits plus 1 uncertain. Your last one to the right is your uncertain digit. And that's the way a scientist is going to look at your numbers. So if you give them, if you meant to say, but instead you said, they're going to see this one as certain and uncertain. They're going to see this one as certain, uncertain, because that digit's not significant, right? It doesn't have an explicit decimal point right here. Now, if you put that right there, now these are certain and that's uncertain. Okay. Oh, this is a good one. If you measure your notebook or your textbook and you find it to be 39.36 centimeters length and 24.83 centimeters width, how many significant figures can you report for the perimeter? So this type of problem, I like to draw pictures. So if we draw a picture of our textbook, and this one is 39.36 centimeters, and this one is 24.83 centimeters. Then what kind of problem is this? If we're doing the perimeter, it's an addition problem, isn't it? So the rules for addition and subtraction apply for calculations in significant figures. So you would add 2 of these together. These 2, both sides, and then these 2 together. And then we've got 4 significant figures here, 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 and here. That's good. Add them all together, and you get 12, 6, 18. And then 7 and 16 is 23. And then you have 2, so you have 18 and 8 is 26, 27, 28. 2, 4, 6, and 6 is 12. So your answer actually has 5 significant figures in it. So that's the weird thing about add subtract rules. You can't tell from the originals how many you're going to have in the answer. You just have to do the calculation. Whereas with multiply divide, all you have to do is limit your answer to the least significant figures in the multipliers. Okay, how about this one? Rules of significant figures. Calculate this one. All right, now I got a feeling that this one's not set up correctly. Right? There are no parentheses here. So if we use the rules of calculation, we're down to multiply and divide. But how are you going to do that? Right? It's implied that this one comes first. So that should have parentheses around it. And otherwise, you'd have to factor these out. Like that would be this divided by that and that divided by that, then add them together. But that doesn't work in this case. So I'm thinking that we add those together. 68, 7, 6, 1, 14, 74, and we're limited there. So that means 74 is the answer here, divided by 5.10. So 2 divided by 3, we're limited to 2. Oh, they actually want an answer. Okay, sorry, I get my calculator out. $74 divided by 5.1. 14.5098. No, it's not right. Is it? Yeah, that's right. 14.5098. Limited to 2. So it should be 15. Yeah, 15. Okay with that? Further explanation?
The only thing I'm confused about is why we limit this to 2 specifically.
Oh, here?
Yeah.
Oh, when you add them together, you line up the decimal points.
Okay.
And this one is significant because it's a non-zero number. If that were 0, then you'd be limited to here because 0 wouldn't be significant unless you had an explicit decimal right there. So then this is the addition, then we have to round it off because we can't carry this through to the end like I would like to. So when you've got a mix of add, subtract, and multiply, divide, you got to do those separately and then resolve the significant figures that you can keep. Okay. Let's see, those are just following the rules. Significant figures are in there in a number. Okay, you just have to know the rules for this one. Let's see. Here's a complicated one. That times that divided by that, then subtract. I think that's the way that should be done. So actually, these types of problems need to have parentheses built into it. If you had parentheses around this group and that group, then you would know to do this first and then that. Well, it said, no, PEMDAS says you do multiply, divide first anyway, doesn't it? So no, okay, this one's okay. You have to do these first and then that one. And this one, of course, has parentheses in it, so we're good there. Let's see. How about 35? Express this volume in liters. So if you have 781.2 cubic centimeters, we might want to make liters out of it. Cubic centimeters and liters are kind of, they're second cousins. But the key to this one is a cubic centimeter is a milliliter. So you just change it to milliliters. Now you can change it to liters. So milli is 10 to the minus 3. You know, 781.2 times 10 to the minus 3 liters. And then let's see, you look at your answers and say, okay, the answers are in standard notation. So that's thousandth of, we go 1, 2, 3, 0.7812 liters. Okay. We good? Okay. Let's see. All right. Let's do 37. It's a unit conversion, but it's not a simple unit conversion. It's a complex unit conversion. Notice that with this, let's see, we're starting with 14.7 pounds per square inch. And we want to end up with grams per square meter. So when you have a dimensional analysis problem like this, where you're going to have this change to a unit and that change to a unit, you do one at a time. So we're going to work on pounds first. We're going to convert pounds to grams. Okay. So do we have a conversion? Pounds to kilograms? Yeah, we can do that. All right. Get rid of the pounds. Now we got the kilograms. So what's the relationship? 2.205 pounds is 1 kilogram. Now we convert kilograms to grams. So it's 10 to the third grams is 1 kilogram. 1,000 grams in a kilogram. Okay. We got grams. Now we're going to do meters, square meters. So inches, let's see, what does it give us? 1 inch equals 2.54 centimeters. All right, so we got inches to centimeters, 2.54 centimeters. But that's not square. That's not square centimeters. That's linear. So what do you do then? All you have to do is square it. That squares this, and that squares that. Okay. We okay? Okay. So now we got square centimeters. Now we need to convert, we're headed for meters, square meters. So how many, I'm gonna have to wrap it around here. Centimeters to meters. Oops, excuse me. Upside down, right? We got rid of square inches, but we need to get rid of square centimeters. So this centimeters on the bottom, so it needs to be on the top here. And then meters. So we have 100 centimeters in a meter. But the meters, the centimeters are squared, and the product needs to be square centimeters also. So that's all you have to do. And the rest is just number crunching. So I would start off by squaring this value. So this is 10 squared, so that would be 10 to the fourth. Right. And this would be whatever 2.54 squared is. And you would just say this times that, times that, times that, times that, divided by, divided by that, divided by this squared. And you got your answer. I think I put that one in there just for the square trick. But you can do that with any power. If you know a linear conversion, but you need to end up with a squared or a cubed, and you just put it on the outside, you put it on the outside, the ratio is still the same. If you square or cube anything inside, the ratio is still the same. Okay, let's see if we can skip those. I want to find something unique. This is another multiple conversion. We don't need to do any more of those. This is a chain conversion also of uranium. We know that uranium occurs at 4 grams per metric ton of ore. And this defines a metric ton, which is 1,000 kilograms. At that concentration, what mass of uranium is present in 1.5 milligrams of Earth's crust? It's a pretty small amount. We need to do that. We can. Or do you want to tell me what to do? Don't do it that way. Where are we starting? And what type of problem is this? Is this a unit conversion? Probably, yeah. There are a whole host of problems in chemistry that can be solved simply by unit conversion. Dimensional analysis. So I would start with 4 grams per metric ton and convert the units. 4 grams per, I don't know how you write that. Metric ton. I don't know if there's a special symbol for that. Right. So this is 4 grams of uranium per metric ton of ore. All right, we're going to have 2 different mass measurements, one for the uranium and one for the ore. So we need to keep those separate. So if we're going to convert grams into, well, actually, let's convert Earth's crust. A metric ton is how many milligrams of Earth's crust? So metric ton is 1,000 kilograms per metric ton. 1,000 kilograms. Okay, that takes care of that one. And then 1.5 milligrams of Earth crust. So this could be grams. Oh, it's kilograms, excuse me, and then grams. So 1 kilogram is 10 to the 3rd grams, and then milligrams of Earth's crust. So this is going to be grams, and this is going to be milligrams. So that's another 1,000, like milligram. Takes 1,000 milligrams to make a gram. So that gives you so much per milligram. So let's leave it right there for now. And let's find out how much this, let's see, what is this? So we have different values here. So we're just going to leave it for grams now. And then it looks like we have different units of measure here. We're going to have to modify our answer. Well, actually, we can go ahead and do it this way. If that's milligrams of Earth's crust, but we want 1.5 milligrams of Earth's crust. So 1.5 milligrams of crust times this concentration will cancel the milligrams, and our answer will be in for only uranium. So this times 1.5 will give us, here it is. Did I lose anybody yet? Let's see, 1.5. Then divide by, what do we do with these if we want to make a single? 3 plus 3 plus 3, right? When you multiply exponents of the same root, you add them together. So that's 9, 10 to the 9th. I'm going to divide that. Okay, so I've got 6 times 10 to the minus 9th grams. Okay, so what is that? Well, let's see. 10 to the minus 3rd is milligrams. 10 to the minus 6th is micrograms. 10 to the minus 9th is nanograms. So we store this up in the nano. Do we have that one? There it is, the very first one. 6 nanograms. If it were micrograms, it would be 6,000. No, it would be 0.006 micrograms. Or 6 times 10 to the minus 3rd micrograms. So this is the only one that fits right here. What is this one? CG. Centigrams. 100th of a gram. We don't use that one too often. All right. Set this down again. I need 4 or 5 hands. Let's see. Okay. Now we've got a density problem. Sometimes you can read the problem through once, but then to really find out what the problem is asking, read backwards. 20.0 mils of glycerol has a mass of 25.2 grams. What is the density of glycerol in ounces per quart? So we're looking for density, but we also want these units. So we're going from metric units to English units. But first we have to calculate the density. Or actually you can solve this problem a number of ways. You could convert milliliters, which is volume, to quarts. And then you could convert grams to ounces. And then calculate your density. Right? Because we know the controlling formula is this one. Mass divided by volume. So if you determine the mass as 25.2 grams, and we want to convert that to what is ounces. Okay, so what have we been given here? This many grams equals an ounce. So that's a simple conversion. 28.4 grams equals 1 ounce. Right? So there's our ounces. That's mass. And then the volume is 20 milliliters. Oops. So what other conversions we get? 1 liter equals 1.06 quarts. Right? So we need to convert this to liters. 10 to the third liters. Gives you liters. Now we can convert liters to quarts, right? So that would be 1.06 quarts per liter. There. Now, they didn't tell us anything else. So we've got to know how many ounces in a quart. How many ounces in a cup? 8. How many ounces in a pint? Well, it's 2 cups, so it'd be 16. How many pints in a quart? 2, so it'd be 32 ounces in a quart. There we go. Now we've got, hold on a second. No, all I needed was quart, wasn't it? I'm confusing myself. This is all we need right here. Sorry. So we got that and that, ounces per quart. It would be confusing if I went to, see, this is weight ounces and this is volume ounces. That's probably why they didn't do it that way, because then you might get confused. So ounces per quart. So now you just do this calculation and divide it by that calculation, and you get your density, which should come out to 41.9 ounces per quart. All righty. You ever wonder about those things that travel really fast? They call those relativistic speeds. When they get close to the speed of light. So what's 93% of the speed of light? Well, if the speed of light is 3 times 10 to the 8th meters per second, then 93% of it, or 0.93, would be your starting place. And then use your conversion factors. 1 kilometer equals that many miles. So I would convert. Do we need to do that one? Should we do that? Or are you getting bored with these? If you're bored with them, that means you know how to do them.
We should do that.
Okay. Give me the go ahead. Okay, so our starting position is 3 times 10 to the 8th meters per second times 0.93, which is the decimal equivalent of 93%. So that's going to be meters per second. And we want to end up with miles per hour. So we're converting this into miles and this into hours. Okay. So let's get the time out of the way. How many seconds in an hour? Well, 60 seconds in a minute, 60 minutes in an hour, so that's 3,600, correct? 3,600 seconds in 1 hour. There we go. Okay, now we can work on the meters. We want miles. So our conversion factor that's given to us is kilometers to miles. So we need to convert that meters to kilometers. There we go. Now we can convert kilometers to miles. Let's see, 0.6214 miles. 0.6214 miles per kilometer. There we go. Now it's just crunching numbers. You multiply this times that times this times that, and then divide by that. You want to do that? Sometimes doing this, I find mistakes in my own documents. So 3, you have to know how to do exponents in your calculator. 3 exponent 8. And then 0.93. And a 3600. And 0.6214 times, divided by 1,000. So I get 6 point, let's see, 93%. So we're limited to 2 significant figures. 6.2 times 10 to the 8th. Here it is, miles per hour. All righty. Let's see. We did one like this in class, I think. Trying to figure out how much money to take along with you to be sure that you can buy gas on the way down and on the way back. So you're going to take a trip that's 2,105 miles away. That's a long trip. If you drive a car that gets 33 miles to the gallon and the gas costs this much, how much will it cost to get to your destination? If you're only going one way, man, where are we headed for? California? That would be 3,500 miles. Or, well, from here, it'd be more like 3,000. So maybe it's Arizona. Okay, so how would we work this one? Well, where do you start? You start with your distance, 2,105 miles. And then you convert it into dollars. So we need to convert miles into gallons of gas. Right, so that's 33 miles per gallon. Notice that it's listed 33 miles per gallon, but we needed 33 miles in the denominator and gallons in the numerator. That's because otherwise it won't cancel. Can we do that? Yeah. Conversion factors are equal to 1. So you can flip it and it's still equal to 1. So you just put the 1 on top and the 1 on bottom that you need to cancel and leave you. And then how much per gallon? What was it? $3.199. And that cancels gallon. And that gives you the amount of money you need to carry to get there. Right? So we're saying it's about $200, which means that the exact calculation here, and I'm curious now, 2,105 and 33 divided into it and times 3.199 is 204 exactly. Actually, 204.06. But if we're going to round it off to conversion factor, those are exact numbers. This is only one that determines. So there's 4, it should be 204.1 or $204.10. So the key here is, let's see, about how much, which is 200. All right. That's another conversion factor. I think we're good to go on that. All right, 49. 29.3 grams of a new element. It doesn't say what the element is, but the question doesn't need to know. was isolated from 660 kilograms of ore, molybdenite. So my guess is that the major element in there is molybdenum. So it'd be, let's see, where is it? Right there. There must be another element there with it. 29.3 grams of the new element. Whatever that happens to be. Isolated from 660 kilograms of ore. We want to know percentage. Well, you can't do percentage with different units of measure in the numerator and denominator. They have to be the same. So we need to take this kilo and make it 10 to the third grams. 660 times 10 to the third grams. Then times 100. I got too many X's up there. Let's call this something else. Element Z. Okay, so 29.3 divided by 660 times 10 to the third, then times 100. And that'll give you the percent by mass of this element, which is 0.0044. And notice, let's see. Okay, that's all right. I was thinking we had a selection in here that would, so lots of times these multiple choice questions are made up to incorporate common errors. So that if you make that error, then you might find your answer in there, but it's the wrong answer. That's how tricky multiple choice questions can be. All right. Kelvin temperature, 409 Kelvin equals what? Either Fahrenheit or Celsius. So what would we do with that one? Well, you take the relationship of Kelvin equals degrees centigrade, Celsius, plus 273. All right, so it's a 409 Kelvin. What is it, Celsius? Well, you minus 273. Solve for this one by taking that one over there minus. So that'd be 631, 136 degrees Celsius. Is that one of them? Yeah. So we don't even have to convert to Fahrenheit. The next one does convert. If your melting point is 391 centigrade Celsius, what is it in Fahrenheit? So what's the formula there? Well, Fahrenheit equals 9/5 Celsius plus 32. So we want to know what it is in Fahrenheit. That's the right formula. Because there you have it. And this one is going to be your value here. So you put 391 in there times 9/5, which is about half of that value. 195, not quite half. 190 plus 32. So which one's close to that? Oh, no, Fahrenheit, excuse me. No, it's not half of it, it's twice that. So it'll be like 632 or 732. So it's either one of these two. Right? So I can't get it by estimating easily. So you have to actually calculate it. Yeah, 2 times this would be 780, but it's not quite 2. So it's in the neighborhood of 732. So there we go. I should be able to do that and answer that question in the test very quickly without a calculator. What do you do when you have a negative value here? You just plug it in the formula. Just be sure you watch the signs. Another conversion, we don't need to do that one. Here's a good one. In 1984, some drums of uranium hexafluoride were lost in the English Channel. which is known for its cold water, 17 degrees. The melting point of uranium hexafluoride is 148 degrees Fahrenheit. What physical state is the uranium hexafluoride in this drum? That's really not a good question. I mean, it requires that you do some calculations, but look, the cold water in the channel is 17 degrees. And if the melting point of uranium hexafluoride is 148 degrees, you can estimate that. You just need to estimate what is that in C, right? If F equals 9/5 C plus 32, we need to find out what C is. So F minus 32 times 5/9 equals C. So let's see if we can estimate this one. If this is 148, that's about what? Well, it's exactly 116, right? And this is about half of that. So it's like, actually it's less than half. So it's greater than half, right? Because this is not quite half. This is divided by a smaller number means it's larger than half. So it'd be in the neighborhood of 65 degrees Celsius, right? So that's the melting point, 65 degrees Celsius, and it's 17 degrees down there. So what state's it going to be in? It's going to be solid. Uranium hexafluoride. Why would you want uranium hexafluoride anyway? The two primary methods for separating isotopes of uranium, 235 versus 238. This one doesn't fission. That one fissions. That's the one you make bombs out of. Or you make nuclear power plants run. But this one is only about 0.5%. So you got to bring up you got to bring that concentration up to over 90% to make a bomb. So one way to do it is, well, actually, both ways to do it, you need uranium in the form of a gas. So in order to do that, you take uranium and convert it into the uranium hexafluoride. And at this temperature, that temperature, or 65 degrees, which is not very high, you convert that into a gas. And then you've got two choices. You can either run it through a diffusion separator using Graham's law. You can separate these two. You have lots and lots of filters. And this one goes through the filter quicker than that one because it weighs less. That's Graham's law. So if you have those filters stacked together and under high pressure, you can push it through filters, and as it goes through the filters, you enrich in this one. Okay, the filters have to be made out of Teflon though, because uranium hexafluoride is extremely corrosive. Stainless steel won't work. It will chew stainless steel up. So Teflon works, and that's one way to purify it. The other way is the way Iran is using that, ultracentrifuges, gas centrifuges. So convert it to a gas and run it through a centrifuge. The heavier isotope migrates to the outside because it has greater mass. And then you suck off the gas in the center and send it to the next centrifuge. You just have banks of these things like that. And eventually you get to weapons grade. When I was a kid, I was growing up in a place called Oak Ridge, Tennessee. And we had two massive factories, plants that were built there. One of them was for the filtration and one of them was for the centrifuge. They were huge. In fact, my family wasn't rich, so for entertainment, we would hop in the car, drive around this thing. It'd take you 15 or 20 minutes. It had a road outside the fence. You didn't go inside the fence unless you want to get shot. But it took a lot of space to do that. Okay. So let's see how we're doing on time. Okay, I've already chewed up an hour. We got till 5, don't we? Okay. Oh, this is a good one. A monolayer of 3.26 times 10 to the minus 6 grams of oleic acid. Oleic acid is a fatty acid. Everybody's got it in your body. It's combined in a true fat. If you have any anatomy and physiology, okay, they may talk about true fats. They're actually triglycerides. So just stick that in the back of your mind until you get to that point. But this oleic acid is hydrophobic. In other words, it doesn't like water. So if you put a drop of it on the surface of calm water, it will spread out into a layer that's a single molecule thick. How do you know? Right? Because you can see through water and oleic acid. Well, you sprinkle talc on the surface. And then when you drop it in there, you see the talc go like that. And then you measure the area of that circle as 20 square meters. So you got this thing that's 20 square meters. Meters, and you've got 3.23 times 10 to the minus 6 grams of oleic acid. The density of oleic acid is given to you. So density equals 0.895 grams per milliliter. What's the thickness of the monolayer? And the thickness of the monolayer is the size of the molecule. So let's look at this. What is that equal to? That's equal to mass divided by volume. So what is it axed to? Volume. The volume of this is what? If you turn this thing on its side, right? What is it? It's a very thin cylinder. Right? And how do you find the volume of a cylinder? Area times height. Height is what we're looking for. Correct? So volume is actually area times height. So now we have a new formula. We have 0.895 grams per mil equals mass 3.23 times 10 to the minus 6 grams divided by area times height. And we know the area. 20 square centimeters times height. So there you go. You got an equation now in one unknown. That one right there. So you solve for that unknown. Which would be what? Well, it's in the denominator here, so it'd be in the numerator over here. You get the unknown on one side and everything else on the other side. So this comes over here to the denominator. 3.23 times 10 to the minus 6 grams divided by 20 square centimeters times 0.895 grams per cubic centimeter. Why didn't I write milliliter? Because milliliters won't cancel. Okay. So we can cancel these two against two of those, which means grams per centimeter. Then this gram is in the denominator, that was in the numerator there. So that means the denominator of the denominator is the numerator. It flips like that. So that means this centimeters is out here. So by analyzing the dimensions, we see that the height is going to be in centimeters. And the answers that you have to choose from are in centimeters. So that's good. So then we just resolve this number, that one divided by that one, divided by that one, and we should get 10⁻⁷ centimeters. So that's the size of the oleic acid molecule. I remember doing this one in high school. I think we went out on the pond. There was a pond right close to the science lab. So we went out there and threw a bunch of talcum powder all over the place. It was a calm day. And then somebody reached out there and first we had to measure what's a drop worth. So we measured several drops. What's the mass of several drops? So like maybe 20 drops, and so the mass of it, so 20 divided into that value is the mass of a drop. Then we put one drop out there. And then we measured the size of and did that calculation. This one's fairly easy. The density of gasoline is 0.7025 grams per milliliter. When gasoline is added to water, what does it do? Float or sink? Floats, right? Archimedes said anything that's less dense than the fluid it's immersed in will float. So it's less dense. Water is 1, right? Water is 1 gram per milliliter. So that will float. Alrighty. Let's see how we did. Let me check now. We go up to 80, chapter 1. Well, let's see if we can skip a few. Let's not skip this one. This is a good one. A piece of zinc with a mass of 12.14 grams is submerged in 46.3 cubic centimeters of water in a graduated cylinder. So this is before you put the zinc in. After you put the zinc in, the volume is now 48 centimeters, cubic centimeters. What's the density? So when you're determining density, when you're going to determine density for a sample, right, you need mass and volume. Well, we got mass. How do you get the volume? Well, if it's a regular shape, you can calculate it by various geometric formulas. If you know the height, the width, and the depth, you can multiply those 3 together. Or if it's a cylinder, you just need to know the area times the height. Or if it's a sphere, then you just need to know the radius. So it's 4/3 pi r cubed. But if it's an irregular object, you need another approach. And in this case, since zinc does not dissolve in water or react with water, we can submerge the zinc in water and its volume is the difference. Right? It'll displace the water. In order to use this method, the object that you submerge in the liquid must be completely submerged. If there's only part of it out of the water, then you're not measuring the entire volume of the object. So what's the volume? Well, it's 48 minus 46.3. Cubic centimeters. Isn't that nice of them? It's a solid, so it's going to be grams per cubic centimeter. I already gave it to you. So that divided by mass, 12.14 grams, equals whatever. So this difference here, delta V, change in volume, goes into this formula. And it turns out to be 7.1 grams per cubic centimeter. What if you have you want to do the density of a liquid? Well, liquid's even easier. You just put it in a graduated cylinder and measure its volume. Okay. I think we're going to do that on not this one, but the next one. Lab techniques, I think. We're going to measure. Yeah, I believe we measure densities. Okay. Let's see. Let's see. Difference between physical change and chemical change. The key to that one is the identity. If there's a chemical change, then the identity of the products is different than the identity of the reactants. If it's a physical change, then the identity of all the materials is the same. It may have changed particle size, it may have changed phase, but it did not change its identity, such as frozen water melts, ice melts, and then more heat makes it into steam. It's still water. But if you drop, if you try to determine the volume of a chunk of sodium, and you drop it in water, you won't be successful because sodium and water are a violent reaction. So they change identity. Sodium reacts with water and produces hydrogen gas plus sodium hydroxide. Okay, so boiling water is a physical change. Let's see. About this one. What is a substance with constant composition that can be broken down into elements by chemical processes? I think that's a compound. The key here is chemical processes. It can only be broken down into simpler substances, elements in this case, by this chemical process. If that's the case, then it's not a pure element. It can be broken down into elements, different elements, by chemical processes. That means it has to break bonds. And if you tried that with, if you tried it with pure iron, nothing would happen. You could decrease this in size until you get to 1 atom of iron. But there are no chemical processes involved. It's all physical. So if you broke this one down, you took rust, broke it down, you could get iron and oxygen, probably like this. Gas. That requires chemical process, chemical change. That means the starting point was a compound. Let's see if we can pick out which one of these separation methods for mixtures employs a system with 2 phases of matter, a mobile phase and a stationary phase. The reason I picked this one out is because I don't think I went into a lot of detail on this one in class. This is known as chromatography. You have a stationary phase and a mobile phase. It's based upon the affinity of the dissolved substances in the mobile phase. So if you have a column and it's packed with stuff, solids, we used to use aluminum oxide, very pure aluminum oxide, granules. We'd pack this tube and we'd have a plug down here with a spout. And then you'd here usually had some packing up here so that when you poured your sample in there, it wouldn't disturb the surface. But it would not absorb your material either. So you pour your stuff in here and under gravity, it would just filter down through. Well, on its way, the X's, so you have X's and Y's together. So the X's are more strongly attracted to the stationary phase, solid stuff. Then they would track slower than the Y's because they're spending time on the stationary phase. They're going to it and away from it, to it and away from it. Takes them longer. So actually down here, you get X's here and Y's there. And then these are known as fractions. So this fraction comes out first because it's less attracted to the mobile phase, to the stationary phase. It spends more time in the mobile phase, which means it's moving faster. That's one type of chromatography. This is column chromatography. Now, one time when I did it, the components that I was separating were colored. So in a glass tube like that, I could watch them separate. And that made it easier to catch the fractions because I could see when this fraction was coming. That one was still up here and this one's coming down here. So I'd catch it right here and I move it away and let it drip for a while. When the next one comes down, I catch it with a fresh beaker. Sometimes that's not always the case. Sometimes your compounds are colorless. In that case, you need a fraction collector. And it just periodically, it just sticks another tube under there and then it goes to the next tube and it goes to the next tube. And then you have to go in and analyze and see, all right, where's the highest amount and how far can I go? Which tubes can I need? Combine them and then you get your product. Or let's say your product, your fraction is fluorescent with UV light. You just turn the lights off and get a black light and you can actually see it come out. There are various tricks. Okay. You know what a pure substance is. Right? Can't be broken down by physical means any further. So you can make pure water by distillation. You can separate water from salt. Get pure water, or you can have pure elements. Right? And in case, if you have pure elements, it depends on what you start with as to whether it's a physical or a chemical means. But elements are pure substance. Compound could be a pure substance, pure water, carbon dioxide, all of them are pure substances as described. What's a solution? It's another name for a solution. A homogeneous mixture. So that's why you can call brass a solution. It's a solid solution of nickel and copper. All right. Oh, here's a tricky one. Let's see. It's got a picture that goes with it. Let's see if we can explain this one. Let's do the first. We'll do 70 first. So you got these pictures here, and you have to sort of understand what they mean. Each one of these circles or squares is an atom. So these are all one type of atom. Here we've got two different types of atoms. Here we've got one atom of one and one atom of the other combined in a molecule. And here we've got the possibility of, actually it looks like this is a mixture of a molecule of these two atoms and a pure element here. And then you've got mixtures of two types of atoms here. Okay, which best represents a homogeneous mixture of an element and the compound? So you look at this and say, okay, if it's a mixture of an element and a compound, we look for the ones where there are compounds. Right? So there's a compound, no element, that's out. There's an element, no compound, that's out. No compounds here, no compounds there. It has to be E. There's no other choice. Okay? So the key to this one is understanding what's meant by those pictures. Oh, 71 is, which is a gaseous compound. In this one, you need to understand what a gas is. Well, a gas is one where the particles are really far apart. So we're looking at this one or that one. So this one is, let's see, what did it say, 71? A gaseous compound has to be this one. C. 72, which represents a solid element. Okay. Solids are going to have, we're going to have a single colored dot or square, right? So actually, there's only one that fits, this one right here. But also, it's a solid because everything's very close together, regularly spaced, everything's locked in place. That's a solid. And 73, which represents a heterogeneous mixture of two elements. Okay. So we need two elements with no compounds. So we got to get rid of this one, we got to get rid of that one. Heterogeneous mixture of two elements, did it say? I bet it's this one. If you look, heterogeneous means sample it anywhere and you get a different number of each of those elements in there. This satisfies right here. This cannot be heterogeneous because it's a gas mixture. All gases are solutions. Well, if they're mixtures, they're solutions. If it's a pure gas, then it's not a solution. It's a pure substance, like this one. But this one is a mixture of those two. And it's a gas, so it has to be a solution. It has to be homogeneous. So this one's the only one that would work for T, for 73. Okay. So let's see, we might ought to get on to chapter 2 here pretty soon. Yeah, this is repetition. How about this one before we leave this topic? The wavelength of a red light is measured as 655 nanometers. How much is that in centimeters? Well, the quick way to do it is to say, what's a nano? 10 to the minus 9 meters. Right? And then, how many meters in a centimeter? Or how many centimeters in a meter? 100 centimeters in a meter. So now we can say 10 squared combined with 10 to the minus 9 is 10 to the minus 7, correct? Right? Add those together. Minus 9 plus 2 is minus 7. And then you look at your answers. All right, scientific notation. So we got to move this one over 2 places, which means this one, that's 10 squared. Squared plus minus 7 is minus 5. 6.55 times 10 to the minus 5th centimeters. Or you can go full-blown dimensional analysis and put another conversion factor out here. That's fine. It works. Okay, chapter 1. What type of separation technique is based on the difference in volatility of the substance to be separated? Distillation. Ask any moonshiner and they'll know the answer to that. Because ethanol is more volatile than water. So you get your mash fermented, you got a mixture of, well, mash, the solid part, but you've also got water and ethanol in there. So you heat it up, and the first thing that comes off is the more volatile substance, which is ethanol. Actually, first thing that comes off is methanol. And you don't want to give that to your customers. You'll either make them go blind or kill them. So that's why a moonshiner will take the still, and when the thumper starts to put out fluid and take the first amount of it, toss it. That's methanol. And you can tell by smell. They have a different smell. Test it until you don't get that methanol smell, you get ethanol smell. They even want to drink it. Check it out. And then you're good to go. Collect everything else that comes off. Okay, chapter 2. Does anybody need to take a break? We're good? Okay. We'll look at chapter 2 now. Let's see, let me remind myself. Atoms, molecules, and ions. Okay. First people to attempt to explain why chemical changes occur were the Greeks. The ancient Greeks tried to explain why chemical changes occur. They weren't very good at it. But they were probably no worse than the alchemists. The alchemists actually didn't worry too much about chemical changes, why they occurred. They just wanted to know the recipes, how things occurred. The first chemist to perform truly quantitative experiments was Robert Boyle. And he did it with gases. How about the law of conservation of mass? Who came up with that one? That was the headless Frenchman, Lavoisier. Well, he did this before he lost his head. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? Right. Remember multiple proportions? You have two components, and if you hold one of the components constant as the same amount, then the second component ratio to its neighbor, in this example 2, will be a whole number of multiples. That's multiple proportions. So we need the two parts, X and Y, to be the same. Right? So here we have ammonia and ammonium chloride. That won't work. Because ammonium and ammonium here are not paired with another chlorine. Right? So that can't work. So here we got zinc and oxygen. Zinc and chlorine, that won't work either. Those second elements have to be the same. How about this one? Hydrogen and oxygen, hydrogen and chlorine? Nope. Aha. Nitrogen, nitrogen, oxygen, oxygen. There you go. So if we hold this one nitrogen constant, then the ratio of the other two are whole numbers. So this one is twice the mass of that one. Okay? That's multiple proportions. What's the one we skipped over? Law of definite proportions. That was Proust. He said that every compound has the same ratio of elements by mass, no matter what the source. It can come from any place. If it's a pure compound that you've isolated, whatever the source, it will have exactly the same mass ratio of elements in it. Now, who finally explained all those things? Those are laws. Who finally put a theory together that explained them all? I'll give you a hint. He was an Englishman. John Dalton. The atomic theory. He explained all of those laws with his theory. Okay, let's see. Oh, 7's a good one. We can actually use the law of definite proportions to predict how many grams of carbon would be present in this sample. If we know the sample of chemical X is found to have 5 grams of oxygen, okay, 10 grams of carbon, let's see, carbon, 10 grams carbon, and 20 grams of nitrogen, right? The law of definite proportions would predict that a 70-gram sample, so we got 70 grams over here of that whole compound. How many do you have here? 5, 15, 35? 35 grams total. So that's the mass of this one. So ratio the carbon to this one. If this is 35, that's twice the mass, right? So carbon should be 20 grams. Definite proportion. Right there. Actually, that should have a decimal right there. Let's see, add these together. Oh, line up the decimals, 35, 70. All right. So we're not paying close attention to our significant figures in this calculation. So the rule here is pick the best answer. And the best answer is 20 grams. Okay. What's that next one? Water and what's this one? H2O2. You ever look on bottles in your medicine cabinet to see what's in them? Check the one that's in a brown plastic bottle. Hydrogen peroxide. Yeah, that's hydrogen peroxide. According to the law of multiple proportions, the ratio of hydrogen atoms per gram of oxygen in hydrogen is what? What ratio? Grams of oxygen in H2O to hydrogen atoms per gram of oxygen in H2O2. Well, let's see. If we hold the hydrogens constant, then the oxygens are going to be a ratio of 1 to 2. Or they're backwards, 2 to 1. According to the law, the ratio of hydrogen atoms per gram of oxygen to the ratio of hydrogen atoms per gram of oxygen here. Okay, I see what they're getting at. If we ratio grams of hydrogen per gram of oxygen over here, they're going to be bigger, right? Because you've only got one oxygen. So the ratio of hydrogen to that one oxygen is one value. The ratio of these hydrogens to those two oxygens is going to be exactly half of that. So then the ratio of this to that would be 2 to 1. That's why it's 2 to 1. If we looked at it the other way, the way the definition was given, then we hold hydrogen constant. And then the oxygen ratio would be 1 to 2. Right? So the way you have to pay attention to the way it's worded, which is not the best for this question. Which of these statements of Dalton's atomic theory are no longer true? Well, let's see. Elements are made of tiny particles. That's still true. Okay. Atoms are not created or destroyed in chemical reaction. Well, that's true. Wait a minute. Is that part of Dalton's atomic theory? Well, it's still true based on the theory. Okay, so it's all right. All atoms of a given element are identical. No. Not since we discovered isotopes. And then atoms are indivisible in chemical reactions. That's true. It takes a nuclear reaction to split up an atom. All of these statements are true according to Monroe. No, they're not. So we did find our answer right here. All right. The chemist credited for inventing a set of symbols for writing elements and a system for writing the formulas of compounds is who? We didn't talk about this in class. It must be in your textbook. So whose idea was it to just use letters? It was this fellow right here, Berzelius, who's a Swedish chemist. In those days, in early 1800s, I think, Sweden was very active in chemistry and physics. Well, just look, well, where did dynamite come from? Came from Alfred Nobel. He was a Swede. What about Avogadro's hypothesis? Let's see which one works. Each atom of oxygen is 16 times more massive. No. A given compound always contains exactly the same proportion. No. When two elements form a series of compounds, the ratio of masses. No. We know this one is multiple proportions. At the same temperature and pressure, equal volumes of different gases contain an equal number of particles. Exactly right. If the volume of two containers is equal, temperature is equal, pressure is equal, we know that the number of particles of gas in each container are exactly equal. That's Avogadro's hypothesis. The first scientist to show that atoms emit any negative particles was J.J. Thomson. He identified the electron, and he actually calculated the ratio of charge to mass. Let's see. All right, one second, let me scroll up a little bit. Many classic experiments have given us indirect evidence of the nature of the atom. Which of the experiments listed below did not give the results described? Right. So Rutherford's experiment proved the Thomson plum pudding model of the atom to be essentially correct. No, Rutherford debunked the plum pudding model in favor of the nuclear model. Right. So we found our answer. All of the above gave the results described. No, just this one is wrong. Did not give the result described. You have to be careful to read these questions. That's okay. You should always be wary of multiple choices. They are designed to confuse. That's their primary mode of operation. Confuse the reader. So you need to really know your topic in order to thwart their efforts to stab you in the back. Okay. Let's see, scientists whose alpha particle scattering experiment, oh, well, that was Rutherford. Discovered the nuclear atom. Oops. Let's see. Now we've already done that. Let's see, which statement is not correct? The mass of an alpha particle is 7,300 times that of an electron. I guess. I don't know. The alpha particle is a helium nucleus, so it's got two protons, two neutrons, and it's got a charge of 4 plus. 2 plus. 2 plus. Yeah, 2 plus. So it's pretty massive. An electron. The electron is about 873 of a proton. So let's see. This one's going to be 4 times that. Yeah, it's about 7. Yeah, that's right. 7,300 times that of an electron. That makes sense. So the key is knowing what this ratio is for an electron. This is equal to the mass of an electron. An alpha particle has a 2 plus charge? Yep, sure does. 3 types of radioactive emission are gamma, beta, and alpha. That's true also. A gamma ray is high energy light. That's true also. So far, we're 4 for 4. There are only 3 types of radioactivity known to scientists today. That one is false. We used to know that it was just these three types, but there are other types of radiation now, in addition to those. And I know we didn't discuss those in class, but take my word for it. There are more than three. In fact, there's one emission. It's got the same mass as an electron, but a positive charge, called a positron. In fact, there are some places, I don't think we have one in West Virginia, or we might have, maybe at a university hospital. The PET scan uses positron emission tomography. That's what that stands for. It's used for non-invasive diagnostics of stuff going on in your body. Okay. So let's see here. So bromine exists naturally as a mixture of bromine 79 and 81 isotopes. That's a statement. An atom of bromine 79 contains what? Well, are you given enough information to do that? No, you got to look it up. That's why you need a periodic table. So you find bromine. You know what the bromine symbol is or where it's located? It's a halogen, right? So it's going to be in this family right here. And there it is, bromine. 35 protons. So it has 35 protons. That means 35 is right here. And then 35 protons is good. So it could be this one or it could be this one of those two. How many neutrons? Well, if it's 79 here, neutrons would be 44, correct? Protons from mass number is neutrons. So 44 neutrons, 35, 44 neutrons, 35 electrons. It's A. If it's a neutral atom, the electrons and the protons are equal. All right. So let's keep this boat moving. I almost skipped that. Which of the following represents a set of isotopes? So you compare them, right? So which one would be an isotope of another one? We'll start with the first one. So is there an isotope related to one? Well, you look for the same number of protons, right? So there you go. Same number of protons, different neutrons. So these two go together. Okay, how about the next one? 21 protons and 19 neutrons, 21, 21. Here we go. 2 and 5, because they have different neutrons, same protons. So 2 and 5. And 22 is left, Roman numeral 3 is left out in the code. There's no other element in there. This is backwards. 18 protons. There's no 18 protons in there. Right. So it's left out. That means it's 1, 4, and 2, 5. 1, 4, and 2, 5. There you go. That's a set of isotopes. What can you tell if you know the number of protons in a neutral atom? Well, you know the name of the atom. You can find out what the atom is, right? And you know the number of electrons. So you can do B and C, which is 2 of the above. So D is the answer for that one. Which of the following statements are true of uranium-238? Its chemical properties will be exactly like those of uranium-235. For the most part, yeah. I'd say that's true. One is true. How about this one? Its mass will be slightly different from that of an atom of 235. Yeah, that's true. It will contain a different number of protons. Nope, That's false. They have to have the same number of protons. More plentiful in nature than uranium-235. Well, yeah. So 1, 2, and 4 are true. An isotope of X has an atomic number of 15 and a mass of 31. Atomic number of 15 and a mass number of 31. So what can we say about that? Well, if it's 15, let's say it's phosphorus. We know that. X is an isotope of phosphorus. That's true. X has 16 neutrons. Yep, 15 from 31 is 16. X has an atomic mass of 30.973. Well, we can't tell that from there. Can we tell it from the periodic table? Yep, as a matter of fact, we can. So is E the answer? No, we're saying D. So it must be based upon an isotope of a particular element is this. So we're saying that we're only looking at that one isotope. The atomic mass that's in the periodic table is a weighted average of all the naturally occurring isotopes. So we can't say, this one we can't say about that. We're only looking at one isotope, so that's not right. Did we do that yet? Calculate the weighted average of, where's that coming in chapter 3?
Stoichiometry. But we probably should have done that already.
So if you find the, if you want to know the atomic mass of naturally occurring element, you need to average those isotopes together. So carbon could be, the most abundant carbon is carbon 12, right? And it's 6 protons. Then there's also 13, and there's 14. But 14 is radioactive, so we really don't count it. It's a very small amount. So we take the abundance of these two. You say the fractional amount of this one times 12 plus the fractional amount of that one times 13. Add them together, and that's your weighted average. It's kind of like doing GPA. You give yourself more credit for a course that's worth 3 hours or 4 hours than you do a course that's worth 1 hour. So you'd rather have an A out of a course that's worth 3 or 4 hours than you would one that's only worth 1 hour. All right. So here's a good one. Calcium 2+ ion. So we need to, let's logically look at this one. It has how many protons? 20. So it's either this one or that one or that one. How about neutrons? Well, it has 20 neutrons too, 20 minus 40 or 40 minus 20. So it could be this one or it could be this one. Right? We threw that one out because it's got the wrong number of neutrons. Then we look for electrons. How do you get 2+ charge out of calcium? You strip away 2 electrons. So the electrons are going to be 20 minus 2 is 18. So that's why this one is the answer. All right. Let's see. Well, this one says, do you know your groups? Which of the following are incorrectly paired? Potassium, excuse me. Potassium is an alkaline metal. That's true. First group. Barium, alkaline earth. Yep, it's in the second group. Oh, it's not a halogen. Oxygen is a chalcogen. So that was wrong. Neon's a noble gas and nickel is a transition metal. So those are true. So C is the wrong answer there. All right, so we get a bunch of those pairing names and symbols. So that's why you need to, at least for this test, you need to know your symbols. Well, actually, you need to know your symbols for the rest of the course. And for all eternity, all these characteristics are of metals, except which one? Metals are good conductors of heat. That's true. Metals are malleable. That's true. Pure iron. If you've ever had a piece of pure iron in your hands, you can scratch it with your fingernail. It's so soft. It only gets hard when you mix a little carbon with it. Malleable, ductile, which means they can be stretched. Often lustrous, yeah, especially if you polish it. Tend to gain electrons in chemical reactions. That is wrong. Metals tend to lose electrons in chemical reactions. Let's see. Now you can do those on your own. Let's do this one, some detective work. You're given a compound that's a metal plus chlorine. It's a metal chloride. Okay? In those ratios, you're told that the metal has 26 electrons. Okay? What's the identity of the metal? Well, let's see. These we know are -1 each. So it has a 2- charge total. So that means this one metal has to balance that charge. It's got to be a 2+. Right? So if it's 2+, that means it's got 2 more protons than electrons. So that'd be 28 protons. Now we can find out where it is. 28, 28, 28. Here it is, nickel. Nickel. Okay. Here what are we doing? Naming compounds. Which of the following pairs is incorrect? Oh, name and formulas. Okay. Ion trichloride. Is that correct? First of all, which one of the types is this? 1, 2, or 3? Was non-metal, correct? So you just say how many there are. 1 iodine, 3 chlorines. Yep, that's true. In this case, remember the convention for type 3s? I said, usually the first one occupying the cation position is to the left. That's not the case in this one. This iodine is below chlorine. So we're actually the one below chlorines. That's doesn't follow the pattern. Phosphorus pentoxide, that's wrong. It's the right type of naming because phosphorus and oxygen are both nonmetals, but you need 2 phosphorus, diphosphorus pentoxide. This is ammonia. It's one of those compounds that has a special name. We wouldn't say nitrogen trioxide, a trihydride here. It's just ammonia. Sulfur hexafluoride, yeah, that's true. So this is the wrong one right here. Okay. What's the correct name of this one? First of all, is it a metal, non-metal? Yep. So it's either a 1 or a 2. How about the metal? Lithium. Where does it come from? Right over there. So it's a fixed charge, 1+. That means all you have to say is lithium chloride. Lithium chloride. There you go. Don't have to say what the charge is. Don't have to say how many chlorines there are. How many oxygens are in this molecule? Actually, it's not a molecule. In this formula unit, there are 8 oxygens. 4 times 2 is 8. Okay. How would we name this one? It's just a calcium ion because it's a fixed charge. We don't have to say what the charge is. It's a calcium ion. and it has to be 2 plus. But this one is a transition metal. It can have more than one charge possible. So vanadium 3 ion would be the correct name for this one. Okay. Let's see. Lots of practice here. Oh, naming acids. Okay. All the following are in aqueous solution. All right. So which one is named wrong? Well, look for oxygen. Okay, so we got oxygen. That means no hydros. No hydro, no hydro, no hydro. Okay, that's part is good. How about sulfuric? This is sulfate, 8 becomes ic, that's sulfuric, correct. Carbonate, CO3, 8 becomes ic, carbonic, that's correct. PO4, 3 minus is phosphate, becomes phosphoric, that's true. No oxygen means we need to start with hydro. Hydrocyanic acid, that's the wrong one right there. Hydrochloric is correct. Hydrocyan, that's wrong. All right. Let's see. Got bunches of names here, naming conventions. Oh, here's a good one. Fill out the chart. So what we've got here is a chart with the symbol over here and the number of protons, neutrons, electrons, and net charge for that symbol. Sometimes the symbol is given, and these that are blue, those are not. Right? So originally, we only had this, that, these two, these three, that one, and these two were given. So we have to figure out the others. Right? So we're given this one. That means if you look in the periodic table, you can find out the protons. You just look for lead right over here. 82, that's right. And this is the isotope of that lead. 206 minus 82 is 124 neutrons. It's neutral, so it means no charge and the same number of electrons as protons. So you can fly through that one. This one is 31 protons, 38 neutrons, and a +3 charge. So 31 protons means you've got gallium right here. Right, so you write the symbol gallium, then you have a charge on that gallium, 3+. Okay. You also know the neutrons, which doesn't matter really. But with a 3+ charge, you need to have 3 fewer electrons than protons, which means you need 28 electrons. Now, if you put in the mass number and the proton, that's fine. But essentially what I need is the symbol and the charge. Well, and this value here. What's TE? I didn't have you memorize that one, did I? TE. Where is it? So here it is. Tellurium. I don't think that was in the list. 52, but you can find it from here. This is given 52. So you look over and there it is. TE is a symbol. And 75 neutrons is given, 54 electrons is given. So 2 more electrons than protons means a 2- charge. Then you put the charge on the symbol. And lastly, you have manganese 2+, and the charge is given here, the number of neutrons is given there, 25 protons for manganese. You just look at manganese right there, 25. 25. So if it's 2+ charge, we have 2 more protons than electrons, you need 23 electrons. So that fills out that chart. And this one is similar to that one in the way you approach it. This, you just write the symbols for these. And then you write the names of the compounds here. Okay. So how do you deduce that one? say, is it metal or non-metal? Is it metal, non-metal, or two non-metals together? That tells you whether it's a type 3 or a type 1, type 2. If it's type 3, you go ahead on and just say how many there are. If it's a type 1 or type 2, then you have to decide, is the metal fixed charge or variable charge? Variable is type 2. And if it's type 2, then you also have to say in the name, what is the charge on the metal? Okay, that's your sequence of operation. And some of them have polyatomic ions in it, like this one, acetate, this one, sulfate, nitrite, hydroxide, and calcium is the 2+ charge, so we need 2 hydroxides. But you don't need to know that to name it, just calcium hydroxide. Okay. Here we're naming the ions, nitrate ion. Well, not the nitrate ion. That's wrong. That negative right there should be a superscript. Make a note. Superscript. Make that correction. Okay, then we have naming compounds. So the more practice you get, the better. Write the formulas this time. Thiosulfate. So this is a polyatomic ion right here. S2O3. There's a 2- charge, so you need 2 pluses of sodium. Let's see. Oh, I didn't show you this one. Acetic acid. There's several ways you can write it. You can write it like this. This is the molecular formula for acetic acid, or you can write it like this, which would be better, I think. C2H3O2. There's only one acidic proton in this group. This one dissociates when you put it in water. These 3 do not. These are so strongly bound into that polyatomic ion that they don't come out. So you've only got 1 acidic proton in this acid. You can write it that way, or this is the way I learned it. It's the same formula, right? 4 hydrogens, 3, 4, 2 carbons, 2 oxygens. This gives you a little bit more information about its structure, because it's going to look like this with hydrogens here, right? That's CH3, and that's bound to carbon. And then this one is like that. And there's your acidic hydrogen right there. CH3COOH is acetic acid. But this is fine. In fact, this would follow the convention a little closer now. This is part of my history. Let's see. We talked about definite proportions already. Multiple proportions, which does not have a Latin symbol. Iron does, copper does. Sodium, N8, natrium, yeah. Potassium. Titanium is the one that doesn't have a Latin derived symbol. Okay, I was just looking for tricky ones now. That's it. And then you have useful information. So the exam that I hand out will have all of these pages at the end. So you just need to know where to find this stuff. Like there's the formula for changing for temperature. It's missing. Yours won't be missing that. This should be degrees F, temperature F. This should be temperature K. For some reason, when I converted this thing to a PDF file, it lost some information. But yours will have all that information in there. let's see, there's your polyatomic ions. And there's your periodic table. You'll have this one and you'll also have that one up there. Let's see, I think that's it. Yeah. Okay, any questions? We'll take a short break and then we'll just stay in here for our lab. There we go. Okay, this lab is one that doesn't require a formal report. In fact, the next one doesn't either. But when we meet next week, I'm going to give you the next one, which is lab techniques. And what I'd like you to do with that one, even though you don't have a formal report, I'd like you to take that one and put it into your lab notebook as if it were going to be a formal report, just to give you practice. Then when you actually do one for a formal report, you'll have a little experience under your belt. But this one, graphing techniques, why do I want to bother you with that? Well, for one thing, humans are visual creatures. When we transfer information, from one person to another, and in modern sciences, that's what you want to do. You want as many people to view your work, your publication, as possible. And you want to convince as many of those people of your position. So one of the ways you can do that is present your findings in graphical form. Sometimes it's easier to make the point if it's in a graph than it is in just a table of numbers. I've seen both ways. And graphs can be almost unimaginably simple or complex. We're going to keep it simple. But you start off with measurements, your data. Okay. Now, if you only have single value data, it's not correlated with anything else, then you can put it in a table. Or you can arrange it some way in a line, maybe. But usually, you're going to have your data correlated with something. In my previous life in agriculture, we always had, not always, but occasionally, and very often actually, we would have crop yield correlated with something that we did to the crop. And in my line of work, it was fertilizer. Put so many pounds of nitrogen on pounds of nitrogen on a crop, and then you measure the yield at the end of the season. Like corn, it might be bushels per acre, something like that. So pounds of nitrogen, but no pounds of nitrogen, you get a certain yield. And if you put 50 pounds of nitrogen, you get more yield. Right? So you get these paired numbers. Well, this is the side that is controlled by the researcher. This is the independent variable. Okay, this is the dependent variable. That's the response to what I did. Okay, and when you put that in a graph in a Cartesian system, right, where you have the pounds of nitrogen here on the x-axis, which is also known as the abscissa, and here on the y-axis, you have the yield. This is the dependent variable. Then you can put data points on here that correspond to that value and that value. So let's say 50 pounds of nitrogen gives you 100 bushels an acre. So we divide it across here, that's 100, this is 50. Then you follow it up here until you found the yield, which in this case might be here, 100 pounds per acre. So your point would be right there. And it would have a value of 50, 100, XY. Okay, and you can do that for this whole list of data. And what's likely to happen is, as you increase the amount of nitrogen, you increase your yield up to a point that it kind of flats out. This is known as direct proportion. As this one increases, that one increases. So let's see, dependent independent variable graph. This is a Cartesian system. Right, X, Y axis. This is the origin. So the value here would be 0, 0. Okay. And actually, you can have, if you need it, you can have negative X and you can have negative Y. So these are quadrants of that graph. If you don't need it, and most of the work I ever did, we never went into the negatives. So it was always in this quadrant. Let's see, what else? Okay, if you have a series of measurements here, and you draw a best fit line. So what we mean by best fit is you draw the best line you can with the least variation, difference between the line and the nearest point. So if you have scatters like this, probably the best fit line is somewhere in there. Now, if we do that, well, let's say this is up there. If we do that, then anything that you, and you can use this line to find out values that weren't actually measured. So we measured this one and this one and this one, but suppose we want to know what would we expect the yield to be if I put this much nitrogen on it? Be right in here or here. We didn't measure it, but from this best fit line, we can interpolate. Inside your measured units is called interpolation. Outside your measured units is extrapolation. Okay. Sometimes your statistical program, if you set the parameters correctly, will draw a confidence interval. In other words, it'll draw another set of lines, one here, say, with about 95% confidence or whatever you set. You know that all the values in your 95% of your values will be between these two lines. So even if your best fit line is there, you may have scatters here. But one thing that's interesting is once you get past the end of your measured values, the confidence limit interval goes like that. So you don't have much confidence outside of that, in the extrapolated region. And that's all statistical. You're not going to have to do that for this exercise. I'm just making a point. So we can also define the nature. Actually, we can calculate a formula for that line. So let's do away with the yield business and just say, let's say we have values here and we have a line. Best fit line looks like that. So how do you describe that straight line? Well, you use the formula. Y equals mx plus b. Everybody knows that one. This is the y variable, that's the x variable. This is the slope of the line. And this is the y-intercept. So there's where b would be, right there. How do you find the slope? Well, once you've got your best fit line, or you can use point. If you got a point that falls right on the line here, right on the line there, then all you need to do is rise over run. Right? So the rise is going to be a change in y, and the run is going to be a change in x. So you just take the value of x here, the value of x there, subtract this one from that one, and divide it into this one minus that one. And you get a measure of slope. Right? So once you've got that one, how do you find this one? Well, you can either look, extrapolate your line to the slope, or you can calculate it. Right? You just, now that you know the slope, plug the slope in, and then find a point on here that falls on the line is preferable. And take those values. What's the x value? What's the y value? What's the slope? Solve for b. And then you can describe your entire line with this. There's a number here, there's a number there, and these are your variables. And that describes the line. Now, not every plot in the sciences is linear. We wish it were, because it's a whole lot easier to describe a straight line than it is a curve. Let's see. Okay, that's a direct relationship. An inverse relationship is one that goes the other direction, like this, or even a curved line would be an inverse relation. All you need is that as x increases, y decreases, and that's true here. If you have, has anybody had calculus before? Calculus, okay, so you know instantaneous slope. The instantaneous slope of this curve would be wherever the tangent line is drawn at that point. That's the slope of the line at that point. But if you come over here, it's got a different slope. That's the thing about curves. They can have different slopes at different positions on the curve. Right? You don't have to worry about that. I'm just making another point. Okay. So before we get to transformations, how to make a curve into a straight line, there are ways for some of them. Let's talk about when you're going to draw your graph. What are you looking for? I mean, what's the best way to draw a graph? Because scientists are not all dullards. We like aesthetics too. It needs to look pleasing in order to draw our attention to the intended point that the writer has. Is trying to convince us of. So you've got your data set, and you've got X and Y values here, all the way down, all the way down. And then you're trying to decide how to draw that thing. Well, you look at the range. Right? What's the smallest and what's the largest number for each one? And then you look at the paper that you're going to draw it on, if you're going to do it by hand. And you say, all right, which one needs more range? Which one needs more space? The one that needs more space should go on an 8.5 by 11 if you can either do it like this, landscape, or you can do it portrait. Right? So if the y-axis needs more space, you would do it this way. But if the x-axis needs more space, you would do it this way. So orientation is important. And then once you've decided which way to go, then you say, all right, how's my paper divided up? Right? It's got, let's see. Hold on a second. Let me scroll down to a blank sheet. Here we go. Well, that's not a good one. Go down. That doesn't say what I wanted to. Here we go. So there's your blank sheet. And notice it's got major blocks and minor blocks. Right? Here's a major block. There. And minor blocks here. So now you've got to decide how you want to stretch your data out. The best way to make it look convincing is to maximize the space that you use. In other words, you don't want to squeeze your data into that little spot right there. You want to spread it out because it's easier to make visual measurements if your graph is spread way out than it is if you try to make it compact. So you take whatever, let's say we're going to use this one. So your X values, maximum values are going to be here. So you want the units, the subunits, such that you maximize your space. Let's say if you choose a unit and your maximum value is going to fall out here, then of course you got to back up. Say use a smaller unit. So you might have to end it over here instead of out here. And then you want something that's convenient. The divisions need to be convenient in a way where you can easily plot your data. So if you've got data with tenths in it, like 10.5 or something like that, tenths, then it might be best, rather than say, these are whole number units here, like this would be 10 and this would be 11, because each one of these is a fifth of that, it's 0.2. So it's more difficult to read. So if you've got the space, then make that 10 and make this 11. Now you've got 10 units in there, and that's decimal, right? So you got tenths available. Let's keep this handy. So the size of the subunits matters. All right. What else? Well, every graph has to stand on its own four legs. In other words, if I extract the graph from that paper and carry it around with me, I should be able to look at the graph, all the information that's contained in the graph, and it should tell me everything I need to know to interpret the graph. Yeah, I don't have to look at the text in the publication to tell what the graph means. The publication is there to say, here's the stuff, and this is what I think it means. But the graph should stand on its own. So you need a title. You need, what does this stand for? It's like, what is the measurement here? So in our case, it would have been like pounds of nitrogen. Or you say the nitrogen applied pounds per acre. That would be a complete description of the measurements that are associated with the x-axis. Now, this one you would say yield. And this would be also pounds. No, this would be bushels, excuse me, bushels per acre. So and then you'd have the units here, and each one of these major units would be marked off. Let's see, 10, 20, 30, something like that. Usually, you don't have to label the subunits. As long as you label the major units, then we can see how many divisions there are between them, right? You don't want to clutter it. So we've got the title, we've got the measurement and its units here, and we've got the points plotted and the best fit line. And then if you have any explanatory notes, you would subscript them. Like you might put a 1 here and then 1 down here. Say something. You probably won't have to do that on yours. So just this stuff would be sufficient. Okay. So let me go back where we left off. Let's see, interpreting graphs, extrapolating, calculate the slope. Okay, we did that. Nonlinear relationships. Okay, we're going to get to this one when we study gases. This is a plot of Boyle's law. And it's a curve. But we're going to use this to show how you could transform curve data into linear data. And it doesn't always work this way. It just happens to work for Boyle's law. There are other types of linear data, and we'll cover them either in this course or the second semester on various other transformations of data. But with Boyle's law says pressure times volume equals a constant value. That's all it does. And whenever you have this, like that, the plot of that, this will be X. He varied the pressure and measured the volume. So that's, well, that's the way he presented it. But this is the independent and this is the dependent. The volume changes as you change the pressure. And this is always a constant value. So if we plot it like that, then you get the hyperbola. Right? Remember from math, what's a hyperbola? Well, you can define it several ways, but this line continued on here never touches that axis. And this one continued on, never touches that axis. That's a hyperbola. So the transformation here we want, what if we divide both sides by volume? Here and here. Like that. We can do that. If you do the same thing to both sides, you haven't changed. So we divide this one by volume, volume cancels out. So now what you have on this side is P, but you got K over V on this side. Well, that doesn't look quite like a straight line. What if we do like this? Factor that V out. Now you're talking. Well, now, what did we say about Y? It was the dependent variable. So in this case, that doesn't quite fit. But we can describe it this way, even though it doesn't fit dependent versus independent. Because now we're saying that this is the independent variable and that's the dependent variable. It's the other way around. But as it turns out, you plot this straight line. And if you plot this one on x-axis and this one on the y-axis, there's your slope. What if we transformed it? Then we'd have to take the inverse of P. That's usually not the way it's presented. In this case, we've got pressure plotted against volume. And then if we go down, now we plot pressure against 1 over V. Now here's the slope of that line is, you can calculate it. But if you use this one to determine some unknown, say if you had, let's see, what if we do right in here, maybe 0.85, then what would be the volume at that pressure? Well, it's not 0.035. 0.035 is equal to 1 over V, right? Because that's the way you drew it. 1 over V. So V would be the inverse of that value. Okay. Now, when you draw this graph, what are the units of measure on this axis? Volume. It's the inverse of liters. If volume is in liters, this one's liters, then this one would be liters to the -1. Okay, that's important. To state the right units of measure. Okay. Let's see. What we doing here? Oh, another possibility. You can do log transformations. And let's see. Yeah, we might do that. We'll get into the log when we talk about kinetics. Let's see, when are we going to do that?
Wait a minute. Are we not going to do kinetics?
Oh, no, I'm sorry. That's 214. Getting ahead of myself. This is 213. So if you come back for the second semester, we'll do reaction rates, which is kinetics. And we use some transformations in there to try to make sense of the data. Okay, let's not get ahead of ourselves here. Let's see. You can have some really weird shapes unless you recognize where they come from and the chemistry behind it. So in this case, there's your title up here. And then here we plot. Okay, that's needs to be shrunk a little bit, I guess. There we go. So this sigmoid curve is actually a titration curve. So the amount of base we add to the solution is the independent variable, and the dependent variable is what's the pH. We measure the acidity of the solution with pH. And this is a buffered solution. So you get up here like this, and the pH doesn't change very much until you get over here, and then it goes up to there. So right in here is the equivalence point for that reaction. And we haven't talked about acid base either, so don't let that bother you. It's just that illustrates that some graphs are not smooth curves, and some are not straight lines, some are sigmoid curves. If you've had any biology, you'll know that this could also resemble a growth curve for some population in nature. Could be microbiological population, it could be mammalian population, for whatever. They start off slow, and then they reach a point where they go, and then there are too many of them. They start eating up their food supply, and they flatten out. That sigmoid curve, you'll see it several places in study of various natural systems. Okay, this is a broken curve. Now, that sigmoid curve and the broken curve are examples of curves that I've given you in extra credit. I'm pretty sure. Let me be sure before I don't want to misspeak. Yes, that's a bonus section. So the sigmoid curve and this broken curve are part of a bonus section. So you try it if you feel like it, you don't have to. How do you interpret this one? When you plot your data, it's going to do this, and then when you mix things together, this line of mixing, you're going to go from this temperature to that temperature fast, right? So you're going to go from here and then up here. And the way you interpret the difference in temperature between those two is you draw a best fit line through this straight portion, and you ignore these. Right? And then you draw this one up here, and where this one ends, you measure that up there to where this straight line intersects. That's your delta T. Okay. So you just need to answer some questions and draw some graphs. I got extra graph paper here. Some of you took some already, but you can have more there if you think you're going to need it. Or you can go on the Blackboard and get the electronic copy, and you can just print off as many sheets as you want. Okay, any questions?